Hey, welcome. How's everybody doing? I am 95%. I'm doing great, plus or minus 0.03. It's a Bayesian joke, sorry. Bad humor is better than no humor, right? Okay, so um, I'm going to jump into starting getting things ready for start talking about material for the class. We're slightly behind. We're in a fine spot. This class always gets slightly behind, but I'm going to jump right into materials. I'll hang around for a little while afterwards if anybody has specific questions, so you can ask them then, or what. So okay, so I'm going to start by sharing my screen. Okay, so we are just kind of where we are in Canvas in the update. We're starting module 3, and so this is this week's live session. Well, we're already in the live session, so it doesn't matter. I mean, it's not worth pointing it out. But what I do want to point out, I did a recording going into homework 1, and that's here. And so that's going to be really important for getting you started on homework 1. That'll make homework 1 much easier. So hopefully that helps homework 1 to make sense. And I'll be doing office hours again this Friday at 1 o'clock. Just checking my schedule here. So I'll be providing more feedback on homework 1. So my high recommendation is you work on homework 1, watch the video.
Continue on, Brett.
Is he gone? Okay. I got here late. What's the video that he was talking about, y'all?
It's
you're in
for homework
charge
1.
now. You should know what it is.
So actually, Nick is on the top left of my screen. So I guess that you get promoted to instructor.
I'm gonna pass that on to someone. Hallie, it was about I guess I'm not because I'm answering the question. It was about the homework 1. Like he posted a video kind of to get the ball rolling with that. Just that assignment.
It was last week's office hours. He went over it a little bit.
Well, thank y'all. Nick, you want to teach us more about Bayesian inference? No.
No.
What I can say is that my prior about my ability to teach this class is about a 0.01. So I can update that by the end of the night. But as of right now, that's where we are.
Y'all think he knows, or do you think he's still just talking into the void?
That's actually a good question. Yeah. He strikes me as the kind of guy that puts Zoom in the background. Doesn't know when it's not there.
It was a pretty abrupt departure. Are you guys having like bad weather in Charlottesville?
Actually, yeah.
Oh yeah, we are.
Just started about less than an hour ago. So that's a possibility.
Like maybe he's sitting there in the dark. God, so-
It is pretty bad. He might have lost power.
For what it's worth, some time ago, I decided to plug in my internet router to my battery back, my UPS backup. So I'll have about 5 minutes of both computer power and internet signal to send out a distress signal once my power goes out. But yeah, that was a recent innovation.
Am I back? Anybody have an idea
You
what
are.
happened? Everything like disappeared for me on Zoom.
Yes, hello, you're back. I think you were disconnected.
Ah, okay. That's weird. Oh, it seems I don't have video, which is weird. I wonder. Wonder if something else has taken over my camera, which would be weird. Okay, I'm gonna try sharing my screen. Can you see my screen?
Yep.
Okay, good. Well, I guess you don't get to see my pretty face tonight, but that's okay. And are you not seeing me?
Nope.
Okay, I'm just getting a gray box for me. So I don't know what that is. But okay, so so let's I'll start it. Plug back in with what I was talking about. So where should we be in this course? This is the slides for module 3. We're slightly behind in material, but that's okay. We usually tend to get slightly behind in the material. And if we need to, I'll record an extra class and post it like office hours or something to cover, or shift the due dates, everything back in Canvas. So if things seem slightly off, just like make your progressions and don't stress if things are, or send me an email if you have any questions on them. Okay. So as you go through things, you should watch all the videos that are in Canvas for the week, read the text for each module. Some of the textbooks are kind of dense mathematical theory books. So, work through them to the best that you can. We're not gonna talk about some of the more technical math things, some of the abstract math things, but the references are really good, and you should get familiar with seeing those and reading them, right? And we have a couple of different textbooks, and they're a little bit different levels, so that's good to get this variety of levels and perspectives. There's also the YouTube videos on Bayesian statistics, and those are from the Oxford. I think it was an Oxford grad student, so we've posted links to those. And this is what actually we're going to go through today. So it's actually not going to be IOU. I'm gonna talk about that. Okay, so where should you be? You should be working on homework 1. And heads up that there's a required assignment in module 3.5. So there's a video and some code. And I expect give a try on that. And we'll do an office hours and address that somewhat in office hours as well. Usually the things in this class wind up being where you put some effort into trying it on your own, and then we'll catch up and do things in office hours that will flesh out any questions. And a lot of stuff winds up being teamwork effectively. So ask good questions on teams, and I'm happy to give answers. Don't worry about giving away secrets. Okay, so here's class recordings. And here's the recording from office hours from homework that I did last week. So I took homework number 1, and I went through maybe 2/3 of it in enough detail to get you on a good spot to get moving on that. I'll do that again this Friday at 1 o'clock. But really what you should do is take the homework assignment, read it and think about it a little bit, and then watch that and follow along. And if you want, watch it for a while, hit pause, write up your answer that follows what I'm walking through, if I get you most of the way through, and then, then watch the next part. And okay, so now we're gonna start content. So we're working off of this Kaggle notebook, and it's the same one we've been working from before. And I'm going to post the link in the chat. By the way, this week I got fiber optic internet, so it's a 1 gigabit per second. I'm super happy. So I can, anyway, I won't bother telling you I'm happy I am about that, but I'm very happy about it. Okay, so this is Bayes' theorem. And just to remind us, this piece on the left hand, this is our posterior probability distribution. What that means is we have some data that's fixed. So we collected some data, and we have some parameters for the probability distribution that's kind of the underlying system. And so that's what this theta represents. We write it as theta. It might be a mu and a sigma. It might be a p. It might whatever it is. Just it's a parameter. But we have a bunch of possible values for that parameter, and we want to be able to assign a probability to each of those possible values. Over here, the top part, this is the likelihood. And here, even though it's x given theta, we think of x still as fixed, but it's written x given theta because it's a likelihood. It's given by the formula that's typical for a likelihood, but the x is still fixed. This is our prior. So if we have any prior information about what the parameters for theta should be, that's what they go. And the bottom, this is denominator. That makes this whole part on the right-hand side sum to 1. Okay, so we started looking into this problem of I flip a coin a bunch of times, and I'm going to catch up to kind of where we were right about here. And I really like working with code to explain things because it's very concrete. Like you have to know what each piece does. Right? Sometimes in notation, you're not sure what something is. And so here, I'll hit run all to run everything in this code. And so here's our situation. We flip a coin 50 times, and P is the probability of heads. And first we looked at P might be 0.5, which would be a fair coin, or P might be, what are the two cases? P might be 0.5, which is a fair coin, or P might be 0.1. So we just have two cases where we're considering. Okay, yeah, so I see. Just taking a question in chat. The only thing that's required to hand in is the let me send an announcement on what's required to hand in module 3. I'll send it out as an announcement over email after we're done here. Okay, so we're looking at those two possibilities. P is 0.5 or P is 0.1. There's yeah, I'll talk about, and I'll send the announcement. I'll send some clarifying things about what things are need to be handed in and what isn't. But so we want to figure out the probability for those two situations. And then what we did is we did Bayes' theorem for not just the fair coin versus the unfair coin, but we considered every X value in this NumPy array, right? From 0 to 1. So these were all the different values for P. If P is 0.5, that's our fair coin. And so we might want to say, what's the problem P is 0.5 versus what's the probability that P is something else? And so here's what the probability is for all those different options, for all those different values. If we flip the coin 50 times and got 21 heads, right? And if we look at 21 out of 50, that's the same as 42 out of 100. So the most probable value is 0.42, right? And then we talked about if it's a coin, you think a coin probably doesn't get heads 42% of the time. A coin more likely gets heads 50% of the time, right? So that's where we're going to get into. That's what we're going to talk about today. How to build in that, we call it subjective information or expert information, because you are all experts on coins. And here we talked about, just a reminder, this was treating this as a discrete probability distribution, and then treating it as a continuous probability distribution. And the difference is that in the continuous case, you want the area under here to be equal to 1. In the discrete case, the sum of all these heights is equal to 1. And the piece that makes the difference is this delta theta, which is the width of a rectangle in the Riemann sum, or plays the role of dx in the integral. Okay, so now how do we include priors? So that's going to be the topic for today. And that's really one of the things that separates Bayesian world from other world, is the ability to include priors. So, okay, so first thing we're going to do is we're going to consider a constant prior. This is also sometimes called the uninformative prior, meaning before we do anything, we have no information, right? Maybe we know nothing about coins, for example, right? Or maybe something we have nothing about. Maybe I try to kick a field goal and I make 50 attempts and 21 successes. And before I go trying to kick some field goals, I have no idea how good I am. I have no prior information about my ability to kick field goals. So that's this case with the constant prior. So let's walk through the pieces. So first, this X, this is going to be the range of all of the p-values that we're going to consider. And if thing I like about working in code, if you're ever not sure what something is, you can always just go and pull it out and print it. And those are all the those are all the different values for p. So we think of it as, we flip a coin, it could take any number from 0 to 1. Like it could be 0.3579824, like any real number, right? Not just integers or the numbers here. But we're going to, because we're on a computer, we have to approximate it with a finite set of numbers. And so we pick this list of 100. So that'll help us do this approximation. Okay, so that's X. Those are the possible p-values that we're going to consider. Our likelihood function is the binomial probability mass function. And it's a probability mass function because for a fixed p, it's discrete, right? You have a fixed and integer number of successes and integer number of trials. So it's a PMF. So what we're doing here is we're taking this binomial probability mass function, and we're saying if I put in 21 for k, meaning 21 successes, and I have 50 for n, that's 50 trials, and I'm going to put in here every possible value for p from this list above. Remember, we're thinking of p is the parameter, plays role of theta. So we want to be able to consider lots of values for that. But our data is fixed. K is 21 and n is 50. Okay, so our prior is going to be a probability distribution, and it's going to have a probability value for each number in this list here. Well, there's 100 lists, 100 numbers. I think it's 100, maybe it's 99, and I think it's 100 numbers in this list. In fact, just to be specific, yeah, there's 100 numbers in this list, right? So there's 100 values of X. They all have equal probability. So the probability that any one of them is correct is going to be, let's just pull that piece out here, 0.01, right? They have the same probability. And so that's why that's called a constant prior. It's the same prior for every possible value. Okay, so here's our denominator in Bayes' theorem. So it's the sum of this likelihood, and just to show us, L is this vector. There's 100 values in it, one value for each of those values of X. These are the likelihoods. And the 42nd term in there is the one that's has the highest likelihood. But if somebody says, oh, the likelihood is 2.978 times 10 to the negative 2, you'd have no idea what that means, right? You have very little idea, right? So what we need, in a way to think of what we do in this, we're rescaling likelihoods to get probabilities. And those are things that we can interpret. Okay, so the delta theta is the width between successive values. So here's delta theta, and another way to say delta theta, we could have computed it as x1 minus x0, right? It's the width of the rectangle in your Riemann sum. It's maybe the step size is what you might call it sometimes. It's the delta x in the sum. But that, including that piece here, makes it so the integral under this curve is going to be equal to 1. Okay, so this is the denominator. And just to be clear about what that is, you run that and then run this. Okay, so the denominator is going to be the same for every different set of the parameters, right? We pick one denominator. It doesn't depend on your parameter. It doesn't depend on which p we're considering. It's a fixed number. In fact, it's a fixed number that makes the probabilities sum to 1 or integrate to 1 in this case. So there's a denominator. Now, this is Bayes' theorem right here. P is a probability distribution on little p, which is our theta, and it's the likelihood times the prior divided by the denominator, right? L is likelihood, this is prior, this is denominator. That is exactly the same as this formula right here. Likelihood times prior divided by denominator, right? That Bayes' theorem is what we're computing below. So, okay, so we hit compute, and then we can plot that. And so this gives us some sense of, okay, I think if I did 21 successes out of 50 trials, most probable value for P is 0.42, right? So it shouldn't be very surprising, but it gives us some sense of what's the spread on possible values, right? We could do a confidence interval here. And in this case, it's called a credible interval because it's on the parameters. Sometimes people say confidence interval, but we could say, okay, my mean is 0.42. I could figure out what the standard deviation is, and I'm 95% confident that the real value for P is plus or minus 2 sigma. Okay, now one of the things we talked about is we could see what happens for different numbers of trials or successes. So suppose I have 500 trials and 210 successes. So I took the same proportion of successes to trials, but just more data, right? And the blue is what we had before, and the red is what we have now with 500 trials and 2010 successes. And I think this is about where we got up to last time. And what should happen? Suppose I increase this further to 1,000 and 420. So same proportion of successes out of our trials, but now I have more data. What's going to happen to the graph, to the red graph down here? The blue will stay the same. That's what we had before, but what'll happen to the red?
The variance should be decreasing, so I think it will just go up. The peak of the graph will go up.
Exactly. Yep. It's going to get narrower. The variance decreases. In fact, we have some formulas for, how that variance decreases as a function of the number of samples.
Square roots of X observations, right?
It is it's related to that. There's a square root of n, I believe, that fits in here.
Yeah, I just remember how variance decreases with the number of time-related observations. It's always square root of time. So since we are showing X number of observations should be a square root of n.
Yep. Okay, so now we're going to talk about expert knowledge prior. So if I tell you I'm going to have a coin, and what would you tell me the probability of getting a heads is? What do you think? What is it most likely?
50%.
Probably 50%, right?
5.
0.5, yep. And so it's not going to be exactly 50%. So what I'm going to do, same set of X's here. I'm going to say, I think it's 0.5, but I'm going to put some kind of confidence around that. I'm going to say it's plus or minus 0.5. And I'm going to, sometimes we talk about the confidence interval. Sometimes we talk about the standard deviation. We can translate between those. So it's plus or minus, it's 0.5 plus or minus 0.06. And I'm 95% confident that it's in that interval. Or another way to say that is my probability distribution on P before picking up a specific coin, just in general, is 0.5 with a standard deviation of 0.03. All right, so there's my probability distribution for getting heads. Now, I'm gonna just ask your opinion, and there's no wrong answer. Do you think that looks like a good probability distribution or a bad one, or why?
Well, it depends for what purposes. It seems a little bit unusable for pretty much anything but the mean, because the tails are non-existent, so we cannot say anything about the tails.
Yeah, so if I picked up a coin, does this kind of represent your belief about how probable it is that the probability of getting a heads is 0.5?
On one experiment,
Just over lots of experiments for that coin, just what the probability of getting heads would be.
yeah, lots of experiment, definitely no. No, there should be
Yeah.
more mass in the tails.
So maybe, I mean, maybe we'd say there's more, should be more mass in the tail, so
It looks like a
maybe.
fair coin, like it's not weighted.
Yeah, so maybe my probability distribution should look more like this. Like, I think it's probably fair, but it's possible that I pick up a coin that's unfair, that's 0.2, only gives me head 20%. Has anybody seen a coin that only gives you heads 20% of the time? I never have, but I think you make a really good argument that this should be a really narrow probability distribution, something like that. Like every coin that I've picked up, I've believed that it gets you heads 50% of the time, plus or minus 0.02, right? I'm really pretty confident it's always that. But let's go with this one that we started with, and we'll come back to what the impact of that
Sorry,
is.
I must have misunderstood you. In a single experiment, in a single run. Yeah, of course, 0.5. But if we do it like in multiple runs, kind of like a game, then the tails should have more mass.
Yeah, then you might. So on that, that would be like what the probability of getting heads is when you estimate it from multiple runs. But we're thinking here, like, what's the true probability of heads for that coin? Like, if you flipped it infinitely many times, what would that P be? Right, we would think it's very close to 1. Yeah. Okay, so we're going to compare the flat prior or the uninformative prior with this expert prior. So what we have to do is just recompute the stuff for the expert situation. So here's our denominator for expert. Here's the probability distribution for the expert, which is this blue curve that we computed up here. And we're estimating this blue curve using a normal distribution, right? It gives a probability for every value from 0 to 1. And then multiply by the delta theta. So this is the denominator for the expert. Here's the posterior probability distribution for the expert case. This is just Bayes' theorem. And then we can plot the two of those together. And so the blue is what we would get if we flipped a coin 50 times and got 21 heads and had no prior belief or understanding of what a coin is. The red is what we would say, okay, here's my belief about the probability for P, right? And this is just a little bit of like a little English language. When I say probability for P is a probability of getting heads. But what we don't care about is the probability of getting heads. We care about the probability of the probability of getting heads. So it's a little like P could be different values, right? Fair or not fair. But we wouldn't let P take all the values from 0 to 1, and we want to find assign a probability to all those different values. So what do you think about this? Does the red seem reasonable? Do you have any like reason to say that red is unreasonable? This is kind of why they're called subjective priors, right? You're all kind of looking at me like, I think so, but I'm not quite sure, right? If you're thinking, hey, 0.5 is what I'm pretty sure a coin should be, and that's pretty much the most likely thing here. Okay, that's all right. There's a little bit of spread. I don't know if companies make non-fair coins. I know some coins, you can look this up on the internet. There are some coins in the world that aren't fair, just by the way they're made. And people do experiments flipping them over and over and over. So, maybe it's the spread of all coins in the world, or is it just pennies, right? There'd be a little different situation. So maybe that's reasonable. What do you think would happen if I came up here and I changed this? If I changed the distribution up here to, let's start with something narrower. So narrow, here's my prior. I'm very confident it's 0.5. What's going to happen if I rerun this block? What do you think? Let's go ahead and find out. So if I rerun this, now the red is the posterior probability distribution with an expert prior. If I did 50 trials and 21 successes, but I put a really strong prior up front. So my prior belief is dominating the data, right? So that's the situation here. So here's my prior, and the data almost gets ignored, right? That looks just a lot like the prior. Let's just, for the sake of being clean, let's leave it like this and then go here. So what I've got below is I have the same setup. The blue is a flat prior. The red is the expert prior with mu is 0.5 and sigma is 0.3. And now I've added this green curve that allows us to play around with either parameters for the data or the prior. So right now, the green is what we get for 500 trials and 21 successes, but the expert prior. So tell me why, what the green, first tell me where's the most probable value for the green? I mean, just roughly.
.41 or something.
Yeah, 0.4, let's see, right here is 0.5. So it's between 0.4 and 0.5, so maybe it's 0.45, I think. I should put nicer grids on these. So I'm gonna say it's about 0.45. Yeah. Because the blue was 0.42 and it seems to be to the right of the blue. Right? What else can you tell me about the green? How's the standard deviation compared to the others?
Standard deviation is less than the blue line, and probably less than the red line.
Yeah, so because we have so much data here, the data is dominating the situation. We have a lot of data, which pushes the mean towards kind of what the mean of the data is, not all the way there, but having a lot of data gives us a confident, like we're highly confident about the value we're seeing. Right? And so hence the small standard deviation. So let's go back to.
But I have like a general question. I thought that in this kind of setup of experiments, prior of your first experiment is actually irrelevant. If you're going to do a lot of experiments, the prior should correct itself if you're updating probabilities, right?
Yeah, so you're one step ahead of us when you say updating probabilities, because we're going to talk about that when you have some information and your prior is based on some set of experiments, and then use an set of experiments for your new data. And so you're kind of a step ahead in the thinking. And you're right. If I based my prior on like 2 coins I found previously, then it wouldn't be a very strong prior. But I've had a lifetime of flipping coins and they always come up, seems 50-50 heads and tails. So I'm going to put a pretty strong prior on that. And that's part of the subjective part. That's part of why kind of people argue against Bayes methods sometimes. Okay, in this case, I took a lot of data and a very narrow prior. And just looking at these values here, I don't know which would win, right? There's always a competition between what the data would tell you and what the prior. And I come over here and I see in green, it's really the prior is dominating this data, right? Because we're getting a very narrow around 0.5. Right. So I don't know, like we could kind of play a game. How much data would I need to overcome that? Well, I can't quite see where the print x at mp.arg max p2. I think that's going to print us. Where is it? 0.5. That prints where the value is occurring. Right. That's what this statement is going to do. So here, even though I've got lots of data that would be nudging it away from that, this super strong prior is pulling it to 0.5. What if I don't know, maybe I'm exceeding floating point precision here or something. Yeah, okay, so I broke things. I wound up dividing by 0 when things are rounded to. Okay, so if I have 50,000 flips of a coin, 21,000 times I come up heads. Even with this very strong prior, I would say, okay, I don't think it's a 50-50 coin. I think it's heads 49% of the time. Right. So, and here, let me give an example of kind of the thing where this is actually what I might care about. Suppose I flip a coin 5 times and I get 2 heads. Let's go 6 times and 2 heads. Right. If you had no prior and you said, I'm going to flip a coin 6 times and get 2 heads, what would you say the probability of getting it heads is? Like if you knew nothing about coins. So 1/3, yeah, 2 out of 6. But we're going to add our prior here and we're to see what happens. Even though this isn't like a super strong prior, remember this is the prior. It's this probability distribution here. It's a prior, to me, looks a little weaker. Like I think we're pretty, if I find a coin, I'm more confident than this is showing that it's going to be a 0.5 50-50 coin. So let's use this. Where is it? Small amount of data with 1/3 heads and a reasonable prior. And what we get is the most probable value is 0.5, and that's where the green is. And this is a really important point. We're going to see this over and over again in a really complicated situations. There was a paper a few years ago in deep learning, became one of the big deep learning papers. But it's this same idea that we're seeing right here, that when you have a prior probability distribution, it can act as a buffer against not having enough data. And we're going to see that like in 8 different places and in 8 different ways. So when you don't really have a lot of data, your prior can be a buffer against getting bad results from not having enough data. Or another way to say that, your prior serves as a form of regularization, right? Regularization is always a way to buffer against overtraining. So having a prior allows you to avoid overtraining. Okay, and here's the last type of prior we're going to talk about here in this block. There's one more type of prior called conjugate priors. Conjugate priors are really important. They're, I think, a little less important for, and Haley asks, does that also mean it can bias your results? Meaning, can the prior bias your results? Yeah. Yep, definitely. The prior can bias your results. And hopefully, if things work, you should get, because it should give you a broad standard deviation or some way that it should tell you, I'm not really certain about this. As long as you started with a reasonable prior, it shouldn't, although it gives you some regularization, it should give you, and this is the Bayesian advantage, that it says, okay, I'm not really certain about this result. You didn't have much data. I'm giving you a weak prior, but it's enough to kind of buffer. So, you know, you can't be too confident. Okay, so here's one more way to set up a prior. And this method is called conjugate priors. And the thing that's nice about conjugate priors is, so we have, in this case, we have a binomial distribution for our likelihood, right? That's the number of successes and number of trials with a p for the probability of success. That distribution is called a binomial distribution. And there's a special type of distribution called a beta distribution. And if you pick your prior as a beta distribution, your prior will play very nicely with your likelihoods. And I'll define play nicely in a minute. But let's take a look at beta distributions here. So if you do a search and you see beta distribution, this plot tells you most of what you need to know. So there's two parameters, alpha and beta. And if they're equal to each other here in this red, like if they're both 0.5, you get a lot of probability near 0 and a lot of probability near 1 and not so much in the middle. So that's saying I have a coin, I don't think it's fair. It's either close to 0 or close to 1, right? If I'm thinking in terms of coins. If I pick alpha is 5, beta equals 1, that's the blue, that's saying I'm pretty sure my probability of heads or probability of success or whatever is not a low number, like a 0.2. I think that's probably out near 0.8 or so, right? That's when the alpha is higher than the beta, that'll push your numbers to the right-hand side. When the alpha is less than the beta, like the green has higher probability to the left-hand side or the low values, right? So when beta is higher, it means I'm more likely to be on the left-hand side. When they're equal, alpha equals 2 and beta equals 2. In this case, I get the purple, which is symmetric. So when they're equal, you're going to get a symmetric distribution here. If they're equal and they're bigger than 1, like this, you'll have your peak in the center and it'll drop off as you go away. If they're equal and they're less than 1, like the red, it goes up, it's symmetric like a smile face. If they're equal and they're both equal to 1, you get a uniform probability distribution, meaning just a straight line across at 1. Oh, and this is one more, alpha equals 2 and beta equals 5. Sometimes you'll get something like what's shown here in this orange, like the probability that it's a 0 is pretty close to 0. The most likely thing is still to the left side, but it drops off slowly as you go to the right. So this picture is nice. It captures all the different situations that you can get. So let's start with, let's start with something from this picture. So the orange is interesting. Alpha is 2 and beta is 5. So alpha is 2, beta is 5. And you'll often see these alpha and beta. Sometimes you'll see A and B. So I pick the parameters here. I'm going to take the same range of values for X, which represents the values for P that we're going to consider. And I say, give me a plot of the beta. It's a probability density function because here, these are the parameters and they're constants and the X is there. So this plot, this is the plot that kind of matches or should match the orange. Oh, I can't quite fit them. Well, that would be pretty if I could. Okay, I'm probably carrying too much, but so the orange, we grab the parameters for the orange, and that's what we get as a plot. Okay, so you could pick alpha and beta to represent what you believe about coins, and then get this. So this is saying, hey, I think my prior says 20% of the times I get a heads, but I'm not real confident about that. All I'm confident is that it's not above 80%. So let's see what that prior gets us. Same thing set up. There's a flat prior and a beta prior together. And here's what we get. So what is the beta prior doing to our posterior? How is it modifying our posterior distribution, right? The blue is if I had no prior. Now, what does this beta prior that we've used do? what happened to the most probable estimate? Yeah, it shifted to the left. So it went
Moved
from
a
about
little
point,
bit to the left. Yeah.
yeah, it went from about 0.42 to maybe 0.4. And that kind of makes sense if you think about the shape of this prior, right? Our belief is more to the left-hand side. What if I make this, let's say 20 and 50? I'm not really sure what that's going to look like. Okay, so you'll notice as I increase these values, I get something with less spread. It's not a normal distribution, so I wouldn't say standard deviation, but I mean, it's true the standard deviation is smaller with these bigger priors. So I could come down here and see what happens. And it shifted further to the left because my prior was narrower. Now I could represent, what do we say I need to do to these parameters to represent something that peaks in the middle around 0.5? Do you remember? And a peak in the center, we want to set them equal. We want to be like the purple, so equal and bigger than 1. So let's go with just exactly the parameters that got the purple back there. So there's our prior. And that prior was pretty weak, right? It was centered, the maximum was at 1, but it didn't shift this very much. And this is still 50 trials and 21 successes. So this prior doesn't look to me kind of what I think about probably getting ahead. So maybe I want to think about that. Maybe that gives me a better estimate that represents my belief about P. And then here's my posterior, and that's reasonable. And when I think reasonable, one of my checks is I'm pretty sure coins are 0.5, and that's in the range of possible values, right? One of the things people do is they take your most probable value, and then you look at 1/20th of that. And anything that's less than 1/20th of that, you just throw away and consider it impossible. That's the same as like a 5% threshold or a hypothesis test. Okay, so here's the thing, though, about remember I said with the conjugate prior, the likelihood function and the prior function play nicely together. And here's what happened. So turns out that if your likelihood function is a binomial function and your beta and your prior is a beta function, then your posterior distribution will be a beta distribution. So let me say that again. If your likelihood is a binomial and you pick a beta as your posterior, then your resulting distribution for your posterior, meaning the left-hand side and Bayes theorem, that's going to be a beta distribution. And all we have to do is look at, okay, here's my K and my N. Those are my parameters. So 21 successes out of 50 trials. And you can put the value for A there, or alpha, and the value for B there, and that'll give you your posterior value for A and your posterior value for B. And then we don't have to estimate anything with Bayes theorem. We just put it in the formula for the beta distribution, right? And the formula for the beta distribution, let's see. That formula is, right, it's this right here or here. It's got a closed form solution, right? There's a formula for it. Okay, so we run this, and what we get is the blue was our flat prior, the orange is the conjugate prior when we estimate it or did an approximation. The dotted line green is the conjugate beta prior from the formula, right? And so this is something people like to use a lot in statistics, because when you set up your prior that way, you get a closed form solution for your posterior. Turns out most of the things we're going to work with in Bayesian machine learning don't have conjugate distributions because the likelihoods are just too complicated, right? So you'll see this a lot, and they make kind of a big deal about it in the Oxford Bayesian statistics. course that we have the YouTube videos for, but we're not going to use it a ton, but it's really important to know about. There's a couple places where it makes things very nice. And so we're going to see those. Okay, so I've got some notes to jump over to. Any questions on the notebook here? Is that helpful? Do you like working in the notebook? Is it okay? Clarifies things. I always like it because it gives me something concrete. Like everything is a
clarify,
number.
For conjugate priors, I thought it's like some kind of like abstract ideal formulation of the problem where you can actually basically solve an equation and find the probability, find the answer. In the real world, machine learning problems, conjugate priors, you will never have them. You actually need to go instance by instance and estimate. Right?
Yep.
So that's what the learning is about.
Yeah, that is a very good description. Yep.
Okay, thank you.
Yep. I lost my pen and then I bought a new pen and I lost that pen. So we're gonna have my clumsy finger for drawing. Fortunately, you only have like 10 or 15 minutes of my clumsy finger drawing. Okay, so topics that we're gonna talk a little bit about theory. First, we're going to walk through priors, and after that, we're going to talk about some theory and Bayesian framework for linear regression, and then Bayesian framework for classification, and really linear discriminant analysis and quadratic discriminant analysis. So we have to finish up the theory around priors, but then after we do that, we get to revisit like classic machine learning things, like quadratic discriminant analysis, Bayesian and linear discriminant analysis, and linear regression, but we're going to take a Bayesian perspective on those. Right? And we'll see what the Bayesian methods give us above and beyond what we could normally previously do. Okay, so let's talk about priors. So here's from the live video lecture notes. Prior, the impact of a choice of a prior, it can be small or medium or large, depending on how narrow of a prior or how strong of a prior that you create. Prior information doesn't precisely determine the prior distribution, meaning I might have some belief about coins, but that doesn't mean we might not all come up with exactly the same resulting distribution, right? We all think probability distribution for P for a coin should have its max of 0.5, but some of us think maybe it's a little more spread, maybe it's a little less spread, and that's okay. So there's that subjectiveness, but there's also different methods for picking that, right? Even if we had the same idea of how narrow the spread should be, one person might use a normal distribution to model the prior, somebody else might use a beta distribution. And so there's these different choices that come into play. So here are the most common choices. The base case, or rates in an existing population. So excuse me, we didn't mention this, but if I had a coin and I had a specific coin from some country and I wasn't familiar with it, and I really cared about being careful, I could flip that coin 10,000 times. Maybe I make a robot that flips it and takes a picture each time and count the heads. And then I could say, okay, the heads is, 10,000 times, whatever, something close to half of 10,000 heads. And I would use that as my prior, right? And that would give you what's the most probable value. We could talk about how that would give you kind of a standard deviation and spread on your prior, but that's kind of considered the golden, kind of the gold standard is to use a base case, right? If we know what the universe looks like. So here's another example. So suppose I want to kick field goals and I want to measure me kicking field goals, and I only get 5 tries. And I make, 1 out of 5. But that somebody did a study that took people my age and took 1,000 of them and had them each kick 20 field goals. And you could make some prior out of that prior distribution for people of my age and health, right? Something like some base population, and you would estimate, okay, this is what this person or this category of object generally does, and that would give you your base case. Subjective probabilities. That's what we did for the coin. Oh, I just think I'll make it up. It's my opinion of what it should be. Hopefully it's an informed opinion. Some people use the word subjective. Some people use the word expert. Kind of depending on whether you want to be derogatory or supportive of the idea of using that a little bit, which term you use. Entropy maximization, something we're not going to talk about very much, but it's worth knowing there's a name there for it. Conjugate priors, which we touched on, we'll go through the detail a little more for those. And then non-informative priors, which are also pretty common. That's when you just don't know. You have no information. I don't want to introduce a bias. Often we take a prior that for a non-informative prior, yeah, we just say everything's equal. Now, in practice, there's a prior that is, or sometimes we just want to say, I really don't know what things are, but I'm gonna guess things are close to 0 or close to 50-50, just to avoid the extremes, right? It's a prior, it's kind of non-informative, but I'm just gonna say I'm gonna avoid the extremes, right? I have, for example, maybe I have no idea what the height of a flower is, right? I don't know what this type of species of flower is, but I think it's probably not 100 feet tall. So I would pick a prior that has maybe a mean of 0, a standard deviation of 50, and I'm only going to consider positive values or something. You see, you could make up a prior that just says I'm going to make the extremes really unlikely. And maybe I should just go ahead and put that in the subjective probabilities case. Maybe, I don't know, the expert prior. Okay, so here's let's walk through a little bit of the math for these. So here's Bayes' theorem. Here's our theta. Remember theta I, that represents just like p. Like we had 100 different values for p that we were considering. So there would be, I would go from 0 to 100, and theta 0 would be 0, theta 1 would be 0.01, and so on. This is our likelihood function. And then here's our prior. And then this is the denominator, right? So let's think about the flat prior case. So where this, since I've got red on here, I'm going to switch to orange, is always going to be just a constant. So suppose we get rid of this and we put a constant in here. Well, let's see what happens if I take this and I put a constant in for that, and I take this and I put a constant in for that also, right? Here's my constants. What's going to happen in this formula?
They are mutually, you can remove them from.
Yeah, we can remove them. Yep, we cancel them. We multiply top and bottom by 1 over c. Yep. And so we just get this. So if you have a constant prior or an unformative prior, all you're doing is taking your likelihoods and then normalizing your likelihoods to sum to 1, right? So that's kind of a nice bit of intuition about what Bayes' theorem is doing. It's normalizing your likelihood, say sum to 1, but you're gonna, I don't want to say bias it, but you're gonna modify that by a prior, right? If you have some prior information. Okay, so let's take a look at the binomial distribution. And here's the formula for the binomial distribution. And here's a beta distribution. And then here's the formula for the beta distribution. And this piece right here is just a term that makes everything sum to 1. So capital B is that. And so the expected value for the beta distribution, we didn't, it's in the Wikipedia page. We haven't talked about why this is true, but the expected value is alpha over alpha plus beta. And in fact, if you want to think about the meaning of the beta distribution, alpha, oh, I shouldn't use a squiggle. Let me make the little. Alpha kind of plays the role of number of successes, and beta plays the role of number of failures. So if I wanted to use previous information to build a beta distribution for my prior, I might say, okay, I had 1,000 people in this person's age health category try to kick a field goal, and out of 1,000, I had 21 successes. So alpha plus beta would be 1,000 and alpha would be 21. So you can really interpret when we talk about beta distribution, it's not something we use a lot, but it's just corresponds to number of successes and failures, or alpha plus beta is a number of trials, right? Number of successes and number of trials in a test, right? And if you remember, we saw as alpha and beta get bigger, those distributions get very tight and narrow, and that corresponds to thinking about if we were estimating it from data. Right, okay, so just like we were talking about, alpha plays a role of number of successes, and alpha plus beta is the number of trials. And when you think about it, by the way, you think about this, it's kind of fun to think about why you get these different types of curves for those. So let's pick the blue one. Alpha is 5. So I have 5 successes out of alpha plus beta trials out of 6 trials. So if I have 6 trials and 5 of them came back as success, I think my probability of being a success is pretty close to 1, right? And that's kind of what this blue, if you think about it, is probability distribution. All of its mass is over here close to 1. It's telling you my probability of getting is probably somewhere close to a 1. Okay. So this is the theorem. This is the big conjugate priors theorem for the binomial in beta, right? And I stated it before, but here it is written out. So if your likelihood function is a binomial and your prior is a beta, right? And here I listed like just the letters for the parameters. Then the posterior probability distribution is going to be a beta distribution. So here's the big part. The likelihood is a binomial. The prior is a beta. The posterior becomes also a beta, right? And in fact, we don't have to do any estimating. We know the closed formula for it, the exact formula for it. Okay, and here's the exact formula for it. The posterior probability distribution is a probability distribution on P is given by that. It's a beta distribution with these parameters. Yep, Dima? Questions? Nope. Okay.
Is there like easy example that shows the binomial and beta distribution? And if you multiply them equals beta distribution. I guess my reason for asking is that isn't it just that your beta prior sums to 1, so that you're basically, like you said, you're normalizing the binomial to be just probability. It's basically a normal distribution, it looks like. But
yeah, so we're going to go through the math now. So I think we're going to answer the question you're asking. Yeah. Now, and this, I'm going to reset this slide. So give me a second to make things pretty. Okay, so let's go ahead. Let's go through a proof of this. Now we could put numbers in and do it as an example, but let's go ahead and prove this theorem. So, okay, so what we do is we take, let's see what our likelihood, we said our likelihood is a binomial distribution. So we have this formula right here for our likelihood. So let's take that formula and stick it in right there. Right, so we know what our formula for our likelihood is. We know what the formula is for the prior, right? We said we're going to pick a prior that's a beta distribution. So let's take that formula and stick it in there, right? There's our prior. So we just take the formula for binomial distribution, formula for beta distribution, we put them there in the top. In the bottom, because this is a PDF, probability estimate function, we have to look at the integral over all possible parameter values. And our parameter value, theta here, is P P. And it's between 0 and 1. So that's why this is this integral between 0 and 1. And remember, this is the bottom is exactly, it mirrors the top, right? And we're integrating over all possible, with respect to P, all possible values of P. So just to kind of highlight what's going on here, P in the bottom, we're integrating with respect to P, so we're going to get a constant. The things that are parameters are going to be these P's in the top, right? In those 4 spots. All the alpha, beta, N, and K, those are all fixed things, which are determined by our data in our prior. Okay, so let's look at, so that's how we set that up. Let's look at this formula here, right? The formula, this is the formula for the posterior. Now, if I just look at the top of that, can you tell me can you find anything that's going to simplify? And it's really just like 1, 2, 3, 4, 5, 6 things multiplied together, right? It's this times that, times that, times that, times that, times that. Right, you can kind of ignore the brackets. So do you see any pieces that are going to simplify? This is one of my favorite slides in this class. It's kind of cool to go through the whole proof of this, but what simplifies? Play Where's Waldo? Yeah, I'll give you
Term, but the under the integral come out, or
the things under the integral. We'll deal with the integral at the end. Yeah. There might be some things we can do with the integral, but what's this piece times that piece? What's P to the K times P to the alpha minus 1? Can you rewrite that as something?
2 or K times alpha minus 1.
Yep, K plus alpha minus 1, but yeah, you got exactly the right idea. Yeah. So, okay, so those will combine to give me this. Do you see anything else in here in the top that's going to combine?
1 minus P.
Yep, exactly. We've got the same thing with a 1 minus P. And so that gives us 1 minus P to the
N minus,
N minus, yep,
P.
K. That whole thing there, right? Now, you mentioned something in the bottom, right? And I mentioned early on, now let's think about the bottom. So P is our variable. So this is an integral with respect to P. So what things in the bottom are constants?
Then
Which terms in the bottom? The bottom is the same thing as the top in the sense that it's like 6 things multiplying each other. Which of those are constants? What doesn't have a P in it?
N choose K.
Yep. So that is a constant. And what else?
1 over beta.
Yeah, that thing's a constant. So we can always just bring a constant through an integral and bring them out. I don't know if that's the kind of thing you were thinking about, John, if you were a step ahead of me. Once we bring those out here, then what can we do with them?
Combine them.
We can combine them, and something simplifies really nicely.
You can cancel them out in the top and bottom.
Yeah, that's fun. That makes me happy. So I can cancel the N choose K. Really, I'll just right here, and then I can cancel this with this. So let's write out what we would get after we did that. Right. So we've canceled, we've combined. And now here's kind of the cool thing. What we have is this formula. It turns out is exactly the same as that formula, right? You kind of have to worry about like the beta, is it really the same? But that beta or that B is this. So what we've proven is that the resulting posterior probability distribution is a beta distribution, right? It was a really easy proof. I mean, there's a bunch of letters running around, but it's a little simplifying, a little canceling, and okay. And so that's, we could rewrite it like this. And so in the posterior, this is your alpha, and this becomes your beta. And so if you have a binomial distribution, you set up your beta prior based on how many successes and failures or whatever you have in your history, or usually from your general population, then you know exactly what your conjugate prior for your posterior is going to be. And if you look at this, remember alpha is the number of successes, right? And so what all you're really doing is taking the number of successes in your prior, which is alpha, plus the number of successes in your data, which is k. And here, this beta term here is the number of failures, and n minus k is the number of failures in your data, and then beta was the number of failures in your prior. So really, the Bayes theorem just gives us a nice way to combine our prior and our likelihood for this setup. Okay. I think we're going to call it a night here. Because I'm 10 minutes over and I apologize. So if you want to take a look at this and think about this example, we're going to start next class by looking at this example. And I uploaded the slides here as module 3 live session slides into our files. Yeah, and that's everything for tonight. And this should help you with homework. Look for this in, like, there's a homework where it has to do with people buying books, and a trial corresponds to a customer that considers buying a book, and a success would be somebody successfully purchasing the book. So this whole framework that we thought about it is right, the pieces that you'll bring in to help the book sales people make decisions.
So is
Yeah.
the best resources for the homework last week's class and office hours, or?
Yep, you're exactly right. Yeah.
Okay.
I'll do the office hours. I designed them to be very helpful for the homework.
Awesome, thank you. And then are you gonna hold them again this week?
Yep. Yeah, they'll be this week, 1 o'clock on Friday.
1 p.m. is that Eastern time?
Yep, 1 p.m. Eastern time. Yeah.
Okay, thank you.
Yeah, you're welcome.
Thank you, Professor.
Good. Thank you.
And then with the notebook, was that in the files section, or was that on GitHub? That one, yeah.
Yeah, this one is on, let's see, we put it in chat. That's probably
Yeah, you put it in the chat.
Oh, you did?
Yeah, the best way to get it is from the chat. I think I've put it in the notes and in class materials a couple of times, but
Well, apologies.
no apologies needed. Yeah, I don't know if I put it anywhere where I like really highlighted like here's a notebook you need. So, but yeah, pull it from the chat now. That's good.
I got it from the chat. Much appreciated.
Okay, excellent. Yeah. Good. Other questions?
Hey, Professor, quick question.
Yeah.
So what are the expectations for module 1 and 2 discussion since the quiz material was pulled?
Yeah. I like the discussions. I don't grade them for accuracy to get a grade, but I read them, and if I see your name, then that's good that I'm getting to know you. So put in a discussion, but if you're busy and overwhelmed that week and you don't put anything in, like, I know I probably shouldn't say this out loud, but there's just not a good way for me to check them. But they're beneficial for everybody to kind of talk about things. So to the extent that it really helps you learn, that's what I care about.
Okay. Yeah, because the prisoner problem and then one of the others, those were in the quizzes. So
Yeah. Sorry about those quizzes. And I think There's a little bit of other material. I have to go through it.
If you took-
Probably from,
Does that just not count anymore? Like if you actually did go and take them, or
yeah, so they don't count anymore.
okay.
Uh,
And what after homework 1 is that the main assignment, or are there other assignments we need for next week?
Just homework 1. And there's this,
What's the assignment after that? It'll be similar, like kind of homework type
yep,
style.
and it's gonna be homework 2. So there's in the class, there's 5 homeworks. There's homework 1, homework 2, etc., up to homework 5. There's occasionally a little small things if they have a number of points with them, like this one's 10 points, then there is something sorry, let me take a look at this. Okay, nope, that's so this it looks like there was a version of our book, so I got to clean up a bunch of the things. Looks like there was a version of our course material that was uploaded from an old one that not everything ported over properly. There are and I think somebody asked about this. There are some things that are listed as that look like an assignment or something, but you don't have to do the assignments. They're not graded. And the short answer is M3.5 has code and a video, and so that's a required assignment. The other things aren't required. So let me just double check this. Yeah, okay, I like that assignment. That's fun. So 3.5 is required. And reading, video assignment, that's required. Video. Okay, this. So some of these are optional, and I really need to make sure that I make it glaringly obvious that these pieces are optional.
And will homework 2 be due?
Yeah.
7th or?
Yeah, so the rhythm will be 5 homeworks. They're each one is going to be assigned the week that the previous one is due, and they take 2 weeks to do. And I guess I shouldn't. Well, okay, I don't know if I should tell you or not. I don't like close them at the day they're due. There's just a lot of people in the course that have jobs or families, and things come up, and you're working on it, and it's a few days after, and that's when you get to turning it in. That said, if you turn it in when it's due, then you can stay in the pace of the class. And the most important thing is don't fall behind, because then it's really hard to catch up. But I don't like mark off for being late and keep a close track of that. I care about more about learning experience and helping you to learn than training you to get things in on time. I don't know. That's just how I like to run it.
Well, I have a 1-year-old in a job, so thank you.
Good. Yeah.
Quick question, Professor, on the office hours. Is it under online meetings?
Yeah, so let me make, while we're sitting and chatting, let me make the office hours here, schedule a new meeting, Bayesian office hours, homework 1, part 2. And that will be this Friday, Um, 1 p.m. for 1 hour, and it might go longer, but that's okay. No, let's make it reoccurring weekly. No, actually, I don't want to make it reoccurring because each time I set it up, I want it to have the name of the homework that we're working on. So if you want to go back at some point and look up some material from homework, it's in that, you'll know which video to go to.
Okay,
So
Thank you.
yeah, good. Yeah, you're welcome. Yeah, thank you. Meeting in the cloud. Okay, so let's just make sure that came up. Yeah, okay, good, terrific. So this Friday, 1 p.m., and that'll be the link. And it'll be homework 1 point part 2. So that'll help you like reference where to go if you want help on those. Good. Other questions?
Professor, did you say you are going to upload today's slide deck, or it's already in the file folder?
Yeah, it's already in the file folder. So if you go to files,
Okay.
yeah. And I uploaded it like right before class and made a few changes. So if you uploaded one earlier today or before, then you probably want to get the latest.
Okay. Yeah, I couldn't find it.
Oh,
Is
okay.
that
So
under module? Oh, it's under the overall.
yeah. So, and you'll notice, I guess I uploaded at 7:14. I should feel a little guilty that you can see that now. Like 1 minute before we started. I guess that's being last
Yeah,
minute.
found it. Thank you.
Okay, good. You're welcome. Good. Other questions? I feel like mystery guy or a lurker or something with no picture on the screen. It bugs me, but oh well. Okay, good. Well, have a great evening. Thanks again, everybody.
Have a good night.
Thanks.
2 things.
Sure.
First, yeah, I'm beginning to feel familiar with the theory. And I'm glad those Jupyter notebooks exist. They exist on Kaggle. I believe we reviewed one last week. Was that right?
Yep.
And it's also
Yep,
on
that's
Kaggle?
correct. Yep, and last week's was also on Kaggle. Yep, that's
Okay, and they're on Kaggle and not in this files listing.
correct.
Okay. I guess another thing was just a follow-up from after class last week, when we were talking about the prisoner's choice problem.
Yeah.
I believe that you suggested that I consider 3 different telling actions by the jailer.
Yeah,
to
did that
prisoner
help?
A. I thought about it for a little bit and wondered, like, isn't it only the case that a jailer can tell one thing? Like, let's say this were an episode from, a detective television show or something. The jailer is only going to tell prisoner A one thing in that episode, you know. So how can I basically consider the probabilities of the like in the Monty Hall problem, each game show, the Monty only tells the contestant one thing, which is a goat is behind this door. So wouldn't it also be the case that in the prisoner's choice problem, the jailer could only tell prisoner A that prisoner C would walk away, or prisoner B would walk away? Like, how
So
can we consider
I
3?
forget what the way it's phrased. Do you have it with you?
Yeah, it's on my local file system at some point. May I have permission to share?
Oh, sure. Yeah. Um, Okay, good. You should have permission.
Okay, I will share the full screen, and that was our preparation of review of distributions and probability review. So this is the same document from last week that we were looking